Good morning. So this is lecture 2 for the mini course on computational metallurgy. Let us see if it works. A couple of weeks ago, a colleague from Greece, Fotis Theolis, asked me to say a little bit more about grain refining effects in magnesium alloys. So I would try to introduce the topic and propose and study it with you and working out some calculations. Let us see if it is interesting enough for you. So um, let us share the screen. And well, in my e-library, I've been asking to the library to get this one, Light Alloys, Metallurgy of the Light Metals. It's a good book by Polmer, St. John, and Makian as well. It's a useful book for students, and it is a very good introduction to the topic. Of course, this is just a course on an introductory course on computational metallurgy. So I would suggest that if you can get the book in your own electronic library, you can have a look at several of these. I can download directly. I can select them all, and I think I can download all the in a zip file all the data from my university library. I will put it somewhere here, but I will not put it into the internet, of course, because it is copyrighted material. And but we can have a look. The one thing that I was trying to introduce you, then I would do it. I've been opening a old commercial, so I cannot open it. It's just encrypted thermodynamic database, which has the extension, which is typical of Pandat and not of other software. So instead of TDB, it is PDB. We have that many elements, that many species, that many 40, more than 400, 446 phases. I think it has been updated and so on. So it is a lot. We do the usual game, so database, we select components, everything, yeah. And then while we are doing other things, we will do all binary phase diagram, and I would like to have magnesium on the left. What can we, I would prefer now, let us, I want to quickly just select aluminum and magnesium, for instance, not silver, but aluminum and magnesium. And then I want to make a phase diagram, but in weight percent. Yeah, okay. So this is what we can do by our hands. I wouldn't use 2000 Celsius degrees. I would just use 1000 here, and then we can produce our binary phase diagram using an encrypted database that you cannot access because you got to buy it, and also you should have also the full software as well. But this is the phase diagram. Let us open a file which is open. I think I have adapted it from the old cost 507, but it is something which is publicly available. So select components, also here, aluminum, magnesium, and do the same game, still with one and then using two different databases. This is one open, so you can have a look and see what's inside. So let us compare copy data. This is commercial and encrypted database, and this is base data. It is not very, very different, okay? But anyway, I believe it will be different from the commercial um, and specific magnesium database and the database, which is basically used by myself for aluminum. I want to see how many difference are there. So let us go back to the previous database. I would load it again. So encrypted database somewhere here, pan magnesium database, select all components here, okay? And then pan phase diagram, calculate all binary phase diagrams, but with magnesium on the right. It will take some time, I guess some minutes. So while we are waiting for the output of the calculations, which normally what I'm doing, they take minutes, maybe more or less, I don't know. We will see. Seems more than I expected, and I should try to close because this is a rather limited resources PC. Let us so now it has generated some of the diagrams, and we will wait. And while we are waiting, we will the download is complete, so I can go back. So we are now um, going back to what we need. So we need some general reference on magnesium. I think um, this could be a good introduction if you are not already experts in the field. We are trying to use general information, and we will recover it and on some course materials or some books or your own experience. We need to say something about what goes on the grain refining effects in solidification. Let me check if in the book there is something. It is, I think, grain. Grain refinement, grains that are maybe refinement. So these are called grain. The element that you see here, zirconium, it is an effective grain refiner, incompatible with silicon, aluminum, and manganese, and removes iron, aluminum, and leather. So this is what we get from experience. But those authors are also expert in many things, especially um, um, David St. John. He has written a lot of things, and also Markian as well, about grain refining efforts and so on. Here you see general features about the solidification. You see whatever you you already have seen from your courses on metallurgy. I would skip most of the important things like this diagram in solidification, trying to apply what we can and concentrate on this growth restriction factor. Um, I would like to concentrate in this table, and for the moment, let us recall what we have just seen. So we will concentrate on this column, which is for magnesium alloys. It could be for aluminum, it could be for titanium as well. Now, these are calculations given a certain concentration in weight C0, given the M coefficient, which is available in the phase diagram, and this other coefficient. So this is the traditional way of calculating those growth restriction factors. And for the moment, we can just state that the higher is this factor, the best for binary systems would be the refinement efforts. For the moment, let us observe it empirically. Of course, it is not just one element, but the combination of elements which is important for grain refining efforts. For the moment, let us consider this one. So let us go back to our window. What's going on? Yes, we are in nickel, not so bad. So what I would suggest you to use, because this is a not for free book, but I would suggest you to look for the paper for Kozlo Schmidt, Schmidt Fetzer. Hope we will find it soon, which is for free. Okay. Let us check if it is sealed for free. Yes. So growth restriction factor in aluminum, silicon, magnesium, copper alloys. Okay. This has been published some 11 years ago, and we can have a look because it is for free. Not all this is open access. So I should put some copy it and send to myself to remember. So we will see the concept that we are interested in, and we will try to do some calculations about that. This is what I am using. So do not be frightened because there is undercooling, there are deltas and so on. But I am saying that this growth restriction factor Q that inversely scales with grain refining, it's something that you calculate from the slope of the solidification curve, because this is T and this is, which is basically related to the child curve. So the child curve, we will use just the derivative of the child curve and using this with the limit of solid fraction going to zero. Seems complicated, but it is not, because we have already seen in the previous lecture that it is possible to do in Pandat, but you could do it by exporting data of your curve. So we would use the numerical derivative at first in Pandat, and then by using this numerical derivative, we will extrapolate to the limit where the solid fraction would go to zero. Okay, I hope I have not been too messy. So these are the commercial info, and then we will do like database. We will load another database. I don't expect everything fits. So load GDB, yeah. We will load Aluminumiani. And we will do the same game we have done here. So select all components and then using all binary phase diagrams, we will set magnesium and we will ask this version of Pandat to calculate everything. And possibly we will leave the data over there. But I would leave to you all so I would just start with a couple of them. Maybe I wouldn't work them all. And I would ask you if you want to participate actively to this course. Otherwise, it's just myself speaking to my screen there. And it is totally nonsense because a course must be interactive, even in a synchronous way, but must be interactive. Otherwise, no sense at all. Otherwise, you would have not a course, but maybe it's better to have a look at the book. Well, so it's going on. So I would close this one there. No, not close really. I would go back to the book where we have been. So grain refinement or grain refinement effects, and we need to work out um, putting them somewhere. Let us see if it is possible decently. Copy and put them, for instance, and no, normally it is impossible. I know that because you have columns and blah, 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 blah. Well, it works. Unbelievable. Oh my, it doesn't work. So we've been copied this, and I would put it somewhere. And so I also should say table 3.1 Polmer, and then what Polmer is the book, but page, any page available seems not. So just table could be enough. So we should need to do those calculations. Let us see. Well, I hope I have not done a mess for our binary. So this we would save in file in my PC, possibly not online. Let us see if it is decent. Oh, Polmer table 3.1. And then, yeah, okay, I would close it for the moment. So Yeah, we are pretty close to the end. Um, in industrial applications, then I would just make, please wait a second because I'm getting the rot. So normally, let us see if you have, yeah, this, that is the, this is a rod. This is a rod of aluminum titanium boron. Uh, it is aluminum titanium 5 boron 1, and it is a grain refiner for many alloys, for many light alloys, sometimes even for copper alloys. So commercially and industrially speaking, you will have ternary alloys like this one, aluminum, titanium, and boron. But at first, we are considering binary effects, and by this kind of calculations like table 1. But then, by computational metallurgy, we can use multi-component. We will limit to 3 for you, but we cannot we don't have any kind of problems because we will use the slope of the child curve for different compositions. Maybe you would suggest them to me. So, which is the time of our recording? I should check. Uh, where we are. Not too bad, 23 minutes. So we are in zinc, and then zirconium, and then that's all. Probably. Yeah, zirconium. It is the last one. So now we want to see overlapping maybe of the first and of the last. So the first, as far as I remember, is aluminum, and the last, as far as I remember, is zirconium. So to see, to have an impression of what, so this is magnesium. No, I wouldn't say silver. I would use. So again, this is something real. This is uh, something that it is difficult to avoid. But any case, copy data from this one, and let us go to this one and enter paste data. Yeah, it seems very good as we have done, practically speaking, before. Then I wouldn't bet a beer that for zirconium copy data would work that good, but let us hope for the best. Paste data. No, it is completely different. Yeah, and so my impression it is not suggested to you. In the recent past, I've been using databases from the National Institute of Standards from Japan, and which is a very good source of binary databases. It is the best in the world. So this computational phase diagram database. So there is just one problem, recent problem, that for some IT requirements and so, they want you to log in using some, would say, public institution account. So you cannot access like it was in the past by using your own Gmail, like I did actually. But now I have registered my university domain even for my students, so I can have access to it if I remember the password. Let us hope that I remember the password. I. Let us try again. Yeah, it worked. So now you have here computational phase diagram database. My contact is Taichi Abe in Japan, and they have done and they're very, very good. You can use. I recommend your own university if you are within the university that you ask them to have access to this database. It is available. So what I want to see, I want to see. So this is magnet. For instance, what we are dubious, it is this magnesium zirconium, and so you can download your database, and normally it works. You have two versions. You have already the phase diagram, but you have also the TDB file. You can download the TDB file. Let us put it here, and let us hope for the best. Meanwhile, where we have, I would say, current workspace, calling it one, two. I should put a new folder, but so we have a lecture 2. And called by Riz. I don't know if it works in English, but save. Yeah, save everything. And close this, then I will compact it somewhere for the next lecture. So I want you possibly to use Pandat Education now that you can use. We have downloaded this one from the NIMS Japanese site there, from NIMS. And so we should rename the file with just TDB extension. And now I believe I can open it using the demo version of Pandat. If possible. Seems not, no. So I made some mess around. This is typical of the mess around you do with the I think I should change properties. Not as we should go into the Windows system. I don't like that much. This kind of activity is totally new. So you should change the extensions and blah, blah, blah. But never mind. I will show you, so, the possibility to load. the pure elements database. So we will select magnesium and zirconium, yes. And then we will just consider a binary phase diagram using, don't be frightened, using the pure elements properties and just their mixing properties. So this is a sort of ideal phase diagram using the thermodynamic properties of both the elements that we have been defining in 1991. And so we have been producing a false, I would say, phase diagram, not taking into account the real solid solution, the real liquid solution, the formation of intermetallic compounds. But database, save, we can save it, and magnesium zirconium, I'm calling it SGTE, then, and then we can open the file open. So you see typical properties. So you, and also the, let's say, the property of a file which has some ideal solution properties. So this has been a sort of a trick, because I would open another file, which is the text file that I have downloaded, and then I have difficulties here to rename, which is the one that I have downloaded recently. And probably I will download again to let me know where it is. So this is good for you, but it's bad for me. So I go back again in this, and also I also stay with the name. So maybe with all, not as a text file, but all files, and then let us see. I am selecting everything. This is very bad for me, but please be patient. And so I'm inside the now Pandat, and I would cut everything here, and I would paste everything, including the copyright, blah, 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 because it is copyrighted material. And so now we do, this is Arroyave Shin Liu, but we will just save current file as mg Arroyave. So you have seen now how it is possible to survive making mistakes, but also it is possible to write everything in text mode and then put into Pandat and then save it like a thermodynamic database. So now I hope we can load it and we can build our binary phase diagram. We can also ask to all binary phase diagram, we have just two elements, so it's quick. Could be also okay if we will work step by step inside the two icons. Mm-hmm. Mm-hmm. It could be like that. So this is the label, the current situation, which is in a way not. I should have a look at the phase diagram book and see what's the real phase diagram. And the real phase diagram, it is not totally, yes, not totally different. Okay, very good. So we can save it here. No, we can save the workspace there, just magnesium zirconium. Oh, no, wait. I want to make the solidification simulation. So we would use 99% and 1% of zirconium. This is the procedure. So you can work out at least to obtain the solidification curve, and then we will stop. Otherwise, you will get your head stuffed. What I would like to have, it is 99% alloy and 1% zirconium, and then we will ask extra outputs, as I mentioned before. So we want to add this function minus t, like we have done in lecture. So the derivative of in the Shai curve of temperature with the solid fraction, and then put the graph there like this one. So we put a phase fraction here and derivative over there with the minus sign in order to keep on the top and see what's going on. So this is Scheil curve, very steep. So it goes from high temperature to low. And then this is also something very, very high. So it would be difficult to go into the limits and see what's going on with this situation, but never mind. We will consider in the next talk. Now we will say the current workspace as magnesium, zirconium, and I will also put 0, 1. Maybe we should correct it afterwards. And for the moment, I believe it's all for your own attention, so I should close Pandat, close this one, and especially stop recording. So thank you for listening, and see you next lecture.